Hello everyone, my name is Mingda Zhang, and today I'm very excited to share our work titled Domain Robust VQA with diverse datasets and methods but no target labels. This is joint efforts with Tristan, Ahmed, Adriana, and Rebecca from University of Pittsburgh. In VQA, the goal is to answer a question under a context which is defined by an image. A successful VQA model needs to extract and process information from both modalities. In the past decade, multiple datasets have been collected and released to support relevant research. However, a widely known issue with VQA models is that they can easily overfit to the dataset bias, thus hard to generalize across datasets. For example, when a model is trained and evaluated on the same dataset, it can achieve satisfactory performance. But when the model is applied to a different dataset, performance usually drops significantly. This problem is known as lack of domain robustness, and it remains a major obstacle that prevents VQA systems from being used in real-world applications. Various domain adaptation strategies have been proposed for visual tasks. However, these techniques cannot be easily migrated to VQA setting due to some unique characteristics. For example, VQA models need to process multi-modal inputs, and reasoning modules are critical to handle complex interactions. In this work, we mainly explored 4 directions regarding the domain robustness of VQA, and we start from a quantitative domain gap analysis. To understand the domain gaps, we sample instances from a pair of datasets and use pre-trained encoders to extract embeddings. The collection of features are then used as representation for the dataset, and we can calculate the maximum mean discrepancy. Specifically, we choose ResNet and BERT as encoders to analyze the semantic domain gaps and show the MMD distances in the table. Here, the large numbers generally mean larger differences. We note that VQA and VQA abstract datasets have very large visual distinctions, consistent with our intuitions. As for the questions, they are very similar, probably because they follow the same protocols during data collection. Syntactically, CocoQA is most similar to JQA because they both use automatic rules to generate questions rather than crowdsourcing. We also note that the syntax and semantics gaps can be very different. For example, syntax of questions in Clever stands out more than CocoQA, but in terms of semantics, they are similarly unique. On the image domain, we can see JQA is different from Clever but is similar with other datasets of real-world images. For the questions, since both Clever and JQA are focusing on compositionality among objects, the domain gaps are much smaller. Next, we leverage some recent advancements in generative models to create synthetic domain shifts. Since most datasets have domain gaps in both image and text space, performance degradation is usually hard to explain. Therefore, we leverage style transfer to generate images of similar content but in different artistic styles, and this restricts shifts to happen in the image space. Similarly, we take advantage of the sequence-to-sequence models in NLP to rephrase the questions in each dataset. Next, we evaluate mainstream VQA models about their sensitivity with respect to domain shifts. We test most recent VQA models of different families, including classic two-stream approach, neurosymbolic approach, and attention-based transformer variants. We evaluate the well-trained models on the synthetically domain-shifted dataset. In general, neurosymbolic approach is more robust to visual domain shifts, while transformers have advantage in question shifts. We also choose MAC and LXMERT as representatives and evaluate the performance degradation of cross-dataset evaluation on real datasets. We observe that performance drop generally aligns with our domain gap analysis. For example, the large domain gaps between VQA v2 and Clever make it very difficult for both models to successfully transfer knowledge. From VQA v2 to VQA abstract and VQA v2 to Visual Genome, we see both models are more sensitive to image domain gaps. By comparing VQA v2 to JQA and VQA v2 to Visual Genome, we see syntactic domain shifts are less troublesome for LXMERT model compared to MAC. Lastly, we will share our explorations for building a domain-robust VQA system without using labels from the target domain. We first try to introduce some mature domain adaptation strategies into VQA setting. In particular, we choose domain adversarial module with a gradient reversal layer and moment matching which regularizes statistical discrepancies. We inject different domain adapters after visual encoding phase, but these achieve only limited success. Inspired by the neurosymbolic approach, we also propose a 2-stage training pipeline to disentangle recognition and reasoning. In this process, the visual encoder and VQA model is optimized in 2 stages separately, which simplifies the optimization and gives more effective domain adaptation. Thank you for your interest.